Hello and welcome. My name is Matthew Querrard, and today I will be presenting diffusiophoretic motion of colloidal particles. This is part of the SURE 2021 Summer Research Program, which was mentored by Dr. Kevin Shanley and Bill Garris. Let's begin by talking about some modern filtration methods. Up first, we have microfiltration, in which it utilizes a porous membrane filter that is pervious to fluid, yet retains a larger sediment. So this sediment could be bacteria, suspended solids. The membrane pores are typically 0.1 to 10 micrometers in diameter, and you can see an image of microfiltration at the top right. Reverse osmosis is very similar to microfiltration, in which a semi-permeable membrane allows for very fine particles to pass through. Usually, reverse osmosis can filter all the way up through to water, unlike microfiltration, and we'll get to in a second, ultrafiltration. But in the adjacent image of reverse osmosis, you can see that as we apply pressure, it filters out that water to have pure water. The water above is filled with substances and colloid, but again, as we apply pressure, the colloid and substances are not able to fit through those pores and allowing for just water to filter through. This is moving water from a low concentration to a high concentration, since the water above the filter has the substances and colloid, therefore a lower concentration, while the water below has a high concentration of water, since it's pure water. This is reverse of what nature likes, which is usually high concentration to a low concentration, hence why we need the pressure. Finally, we have ultrafiltration, which is similar to microfiltration and reverse osmosis. Porous membrane filters separate the suspended sediment from solution. This could again be bacteria, suspended solids, viruses, and the membrane pores are typically 0.001 to 0.05 micrometers. You can see an image right under the reverse osmosis image of ultrafiltration. Next up, we have inefficiencies of modern filtration methods. So since higher pressures are needed to drive the water from those low concentrations to high concentrations, a pump is needed. This can require maintenance costs, installation fees, different costs associated with just having and maintaining a pump. Membrane maintenance is also required, and replacement costs as well. The colloid and suspended particles over time can get stuck on the membrane and build up, therefore not allowing for water to fully filter through. So you need to be able to service it, clean it, repair it. Turbid water is also not able to be filtered through these membranes. The turbid water is water with dirt that doesn't sit in one spot, it flows around. Several membrane filtration methods struggle to filter soluble particles. Again, unlike the ones that we've spoken about already, nanofiltration is unable to filter monovalent ions, and you can see at the adjacent image the different filtration methods with their respective particles that they can filter out. All right, so let's get into some of the objectives of the research. We were to investigate membraneless filtration and what constituents are required to complete the task. We wanted to incorporate some three-dimensional printing to aid in the membraneless filtration. We wanted to perform computer-aided design to get those three-dimensional prints. This was done using SolidWorks. We wanted to collect and utilize data from credible sources, so this was our literature review of going through and understanding the task at hand. We wanted to observe and redesign as necessary until we got to the right solution to the problem. So now let's get into some diffusophoresis, which is the theory. So in a closed chamber, we will introduce a substance, mostly a chemical, into a colloid, causing a concentration gradient. Concentration gradient generates a velocity on the particulate within the colloid. This velocity pushes the particulate towards or away the concentration gradient, depending on the particle-molecule interactions. An image of this is shown at the bottom left. You can see as the colloid suspension flows down the length of the channel, the particle has a fluid motion, a velocity towards that concentration gradient. And with the image on the right, you can see with CO2 and air, as the carbon dioxide is on the bottom, it's pushing up, which pushes those colloids, the dirty water, up through the top surface and the clean water through the bottom. So this will be diffusophoresis, the chemical reaction. The solution containing water and particulate, those are the charged particles, flow through the microchannel device. Carbon dioxide is introduced to the solution at a pressure slightly above atmospheric. This is usually about 1.1 atmospheres. The following equation will relate the chemical reaction that causes inside the microchannel. So we have water plus carbon dioxide will yield a hydrogen ion plus a bicarbonate ion. The conversion of water and carbon dioxide molecules to hydrogen and bicarbonate creates that ion concentration gradient. This will, again, drive those particles in which direction. So these are the different microchannel components and their subsequent applications. At the left, we have the steel-backed membrane. This is the permeable membrane that allows for carbon dioxide to pass through. On the right, we have the CO2 channel, which was made of an ABS material, which is responsible for holding all the pieces in place and allowing for the carbon dioxide to enter through. Adjacent to that, we have the air channel, which was made out of PLA. This acts open to the atmosphere and allows for air to pass through a top membrane. We have silicone tape bands next. This was what created the base of the microchannel and what held everything together. Then we have the CO2 adapter. This allowed for CO2 to enter through. And finally, we have the steel splitter, which would split the water at the end of the microchannel. These are some of the auxiliary components. We used a syringe pump with the syringe. This allowed to keep a constant flow rate throughout that microchannel. We had a CO2 tank, which acted as our reservoir of carbon dioxide. We had the regulator, which regulated how much carbon dioxide entered through the channel. Fluorescent particles will be used to study how much the filtration is effective. So how much particles flow through the second hole. And finally, we have the fluorescent flashlight, which will help view those fluorescent particles in the different solutions. Next, we have the CAD models. Again, these were done in SolidWorks. So at the top left, that is the first iteration that was made. This was meant a much bigger CO2 chamber than what was actually needed, but as designs went through, we changed it very significantly. In the second iteration, we slowed it down a little bit, we shrunk it. The third iteration, we tried to split it up to see if it'll be easier, and all the way through. And with the sixth iteration, we started putting those pieces together and really seeing how they fit together. These are some more iterations that we went through. Seventh and eighth, likewise, we had those different pieces that we stuck together. And finally with the 10th iteration. These are the physical 3D printed models. There's the first iteration at the top left, all the way up to the 7th iteration at the bottom right, with their constituent parts and different materials that were used to print. This was the final design that was chosen. So that 7th iteration on the CO2 chamber was what we went with. You can see at the top right image, there is the CO2 adapter that plugs right into the CO2 chamber. And we have the steel-backed membrane that's porous that'll allow for that CO2 to go through. And we have those red silicone tapes that will house the microchannel and hold everything together. This is the steel splitter that will split the water at the end of the microchannel. And finally, we have the other steel-backed membrane to allow the atmospheric pressure of air. And you can see also the top, this is the air channel that supports that. All right, so now we have a SolidWorks simulation of the flow through the microchannel. And you can see over here, the water is flowing through. And then on this right side, you can see there, this is the splitter. And as it hits the splitter, the water slows down quite significantly. And there is a boundary condition called the no-slip condition, in which that water will stick. So at the top surface, you can see how these ones are moving very slow. Water that is touching the top surface, the bottom surface, and the splitter, the velocity is actually 0. Now this is getting into actually splitting the water. So the silicone tapes that were used for this experiment, the thickness was 20 mil, or 20 thousandths of an inch, or 0.508 millimeters, in a 60 milliliter syringe at a flow rate higher than the nominal flow rate was used. This is to get that water all the way through. Now, in the adjacent video, you'll see the water flow through the microchannel, and if you look at the bottom, you'll see the water start to flow out, and as well as on the top. This is the microchannel actively splitting the water as it flows through. Now let's get into a quick experimentation. Throughout this experiment, there was no microparticles or CO2 used, since we were not able to receive CO2. This research was primarily to understand exactly how the 3D printed materials would work and how well they would split the water. So you can hear the pump running. You can see it at the end, the water flowing through that hole. And these are some of the challenges that were encountered throughout the entire research program. It was very difficult to get a good split. With some of the materials that we were using, we had to go through many design iterations, as you all have seen. We tried using PLA, ABS, different materials to try and help out and make the microchannel watertight. We had to go with silicone tapes at the end, since they stuck to each other very well, because silicone likes to stick to silicone and not many other things. The water also had a tendency to funnel out only one exit hole. We tried very hard to make it exit out both, but we had a lot of trouble trying to make it split evenly. Leaks, again, were also very difficult to manage. They would leak out sides that were supposed to be sealed, and again, since we're using plastics such as PLA and ABS, they are very difficult to make watertight. These are some of the conclusions that were drawn. The 3D printed materials used as the microchannel could not establish a complete seal. Again, we 3D printed some pieces for the microchannel, and it would not seal completely, allowing leaks and allowing not a good split at the end. Silicone tapes and membranes provided the best sealing properties. This is the current design iteration that we have. We have using those red silicone tapes, and so far that was the best seal that we were able to get with the most split. The CO2 channel performed optimally with no visible leaks, so in that latest design iteration we had minimal leaks throughout the sides and through the top. And with that being said, thank you all for your time. If you have any thoughts, ideas for improvements, and feedback, I would love to hear that. Thank you again for all of your time. I appreciate you listening. Take care.